Yeah, so maybe I can begin to introduce myself. Well, first of all, thank you for inviting me and for having me. I hope this talk is interesting to most of you, and I hope it's clear. I will try to present these results in a self-contained way. So hopefully I will take you from never hearing of this before to understanding the final result. And if not, please stop me. And this is work which has been carried out as part of my PhD project here in Germany, in the University of Düsseldorf, and also together with the German Aerospace Agency. By the way, you can see the mouse, right? So if I use like a pointer, can you see the mouse?
I could see it, but I'm not seeing it at the moment. Maybe do you have two different screens? Or wait, what is up? I see it now. Yeah, okay. I see
Yeah,
the.
okay.
Yeah, okay, good.
Yeah, okay. So, okay. Cool. Okay, so this work is based on the role of complex numbers in quantum mechanics. And as many of you know, complex numbers appear in various contexts like mathematics, engineering, physics. They have been around since the 16th century, if I'm not mistaken, or yeah, 16th century, I believe. And yeah, and they are particularly useful in quantum mechanics. And then even the fathers of the theory realized this very soon, that everything we measure and all the predictions that we get are real numbers. So this begs the question of, are complex numbers really fundamental for quantum mechanics, or are they simply a helpful tool? Right. So first of all, in order to give you a little bit of an overview and a review of the literature, yes, the topic of a theory which is called real quantum mechanics, that for short I will denote as RQM, has been extensively studied since the 60s. And first of all, one can distinguish two classes of this generalized probability theory denoted real quantum mechanics. The first class is the class of theories which are equivalent to quantum mechanics. And throughout this talk, the term equivalent will mean that these two theories are experimentally indistinguishable. This is what I mean by equivalent. In other words, that both theories give the same prediction for experiments. This first class of theories, the equivalent class of theories, let's say, achieves this equivalence through the inclusion of what is called a binary real-valued object, often called a rebit. And this is a binary object because it's used to store the information for the real and imaginary component of a general quantum system or quantum state. Right. So this rebit is universal in the sense that it is accessible from all the subsystems conforming a composite state. And then this has been interpreted as sort of non-locality of this rebit. And to give you a particular example, you can imagine a multipartite experiment where you have one of the experimenters locally performing a phase rotation, for example. This will in general change the amplitude of the overall state. In particular, it can be complex. And this would, in this formalism, this would alter the state of this universal bit. And so if another party does the same, they would alter the state of this universal bit. And then this is the non-locality of the rebit. And then I know that in quantum information theory, normally the locality or non-locality term is associated with Bell non-locality. But every time I use this term throughout this talk, I'm meaning this kind of, let's say, local accessibility, if you like, when I say non-locality. Right. And then, as maybe some of you were already guessing, the second class of these real quantum mechanics are the ones that are not equivalent to quantum mechanics. And these ones circumvent this problem of non-locality with a tensor product postulate. And I said at the beginning, but you can really stop me at any point. If you have any questions at some point, you can stop me.
So right. That's a good opportunity for me to already ask a quick question.
That's what I said.
Right. So when you say this rebit, I'm not fully sure, because I guess like you're just saying it at a high level. But how does one model composite systems or composite systems. Well, I do not say in this rebit-like model, or it's
I
not.
think it will become clear in a couple of slides because I will have
I
some
see.
formulas, but essentially you can think of it, you can have your general state of a multipartite composite system, and then you simply attach another bit. And then you put the bit in state 0 for the real part. So you split real and imaginary parts of the overall state, and you attach the 0 state for the real part and the 1 state for the imaginary part.
Okay.
But this is a global, let's say, global auxiliary bit for the
I see.
overall composite system. And this is and this was already known since the 60s. If you allow for theories like this, you can reproduce every single prediction that standard or complex quantum mechanics gives you. This was known.
But then the tensor, so the composition of systems is not under tensor products in this
Exactly.
rebit-like theory.
Exactly. This is the key point, right? And this is why the second models, the second class of real quantum mechanics, are based on the tensor product postulate. Actually, this is what I was going to say in the next slide. And recently, maybe you are familiar with this recent paper which was published in Nature. They showed that this class of real quantum mechanics, which is local in this sense, and which has the tensor product structure, these two theories or this class of theories result into experimentally distinguishable theories from standard quantum mechanics. So yeah, exactly. So basically what they do in this class of theories is they devise a Bell-type experiment, tripartite Bell-type experiment, for which the real version of quantum mechanics gives you different predictions than standard quantum mechanics. But yeah, like you said, this is based on the tensor product postulate. Okay. Yes. Okay. So let me give you a little summary of the postulates because what is a theory at the end of the day? A theory is a set of axioms, a set of postulates, no? So the three of them, the first three of postulates you're going to be very familiar with because they are the standard postulates of standard quantum mechanics. Basically, the state of a physical system is represented by a normalized vector, complex or real Hilbert space. And a measurement in system A corresponds to an ensemble of self-adjoint projections. I mean, I think most of you are familiar with this. Then the third postulate tells you how to measure via the Born rule. And then the fourth postulate, which is the crucial one, is that how do you compose systems? In this paper that I cited before, they take the composite system being the tensor product of the individual Hilbert spaces. Okay, so now what do we want to do now? Can we construct a theory based on real numbers, which is equivalent to complex quantum mechanics in the sense that it is experimentally indistinguishable, which is local? Can we do that? So in order to do that, we start with a very trivial or maybe well-known isomorphism between complex and real vectors for a single party. Let's say one party holding one qubit, and then essentially what I explained before, you split the real and imaginary component, and you attach we denote it by flag, so hence the subindex F. You attach the real part with the state 0 and the imaginary part with the state 1. So far, there are no locality considerations because this is a single party. Right. First, we realize that in standard quantum mechanics, there are certain ambiguities. For example, the two states that differ by a global phase are physically the same state, which means that they are experimentally indistinguishable. If we translate this global phase into our formalism, it's very simple to realize that a global phase translates into a SO2 rotation. So then this U1 ambiguity present in complex quantum mechanics translates into an SO2 ambiguity. But as I said before, these two states here in complex quantum mechanics are indistinguishable. And we would like this feature to remain in our theory. Then what does this mean? So now if we consider this pi tilde and psi tilde as the states in the real formalism, we want these two states to yield the same expectation value over arbitrary observables. And then simply, if you just attach this equation here, this already spits out the condition that flag rotations and arbitrary projections must commute. And in particular, then you just do the calculations, which are not very difficult, but you can believe me that this already imposes you the shape of observables in our real formalism. And here the IF represents the identity matrix in the flux subspace, and JF represents the symplectic matrix in the flux subspace. Right, so for one party, so far so good, nothing uncomfortable happens. So now the next natural step is to go to composite systems. And then for the sake of clarity for this talk, I will consider bipartite systems of 2 qubits, but this is generalizable to arbitrary, arbitrary many number of parties and qubits, but yeah, just for simplicity. Okay, so the first natural thing to do is if you have a map S that behaves well, let's extend it to a tensor product. So let's consider S tensor 2. But then the problems start to arise very quickly. First of all, if you analyze the real dimension of the original space, it's 8, but the real dimension of the image space is 16. So already there is a dimension mismatch. Also, in standard quantum mechanics, complex quantum mechanics, we have another ambiguity, which is the freedom, let's say, to assess a local phase indistinctively to whichever party you prefer. So basically, these states, this strictly speaking is called this tensor product is complex linear. But what happens is that these 2 states under the map S tensor 2 would get mapped to 2 different representations, and this in turn implies that this map is not well defined. As an example, you can consider the state of bipartite state 0, 1, and this state, according to this map, since these 2 vectors are real, gets mapped to the state 0, 1, tensor 0, 0. But you can also consider this state as having an I here and a minus I in front. So then this would give this state, which is in this target space. These 2 states are actually orthogonal. So this is the definition of an ill-defined map. This is bad. What do we do? What can you do is, okay, maybe let's try to extend the inverse map to the tensor 2. And now in this case, this map is well defined because you have 2 elements in the domain with the same element in the image. This is no problem. This only means that you cannot invert this map because the kernel of this map is non-trivial. But then this is a problem because with this inverted map, we are going from real spaces to complex spaces. And what we want to do is the opposite. We want to go from complex to real. But thankfully, there is a standard procedure to invert non-invertible maps. And this is through the quotient space. So first of all, yeah, as I said before, the kernel of this application is non-trivial, so this map is not invertible, yeah. And then you can go to the quotient space, where now elements are equivalence classes. And in the quotient space, essentially what it does is to collapse the kernel to a trivially, and you can choose it to be the 0 vector, and then your kernel becomes trivial, and therefore you can invert. This might not be very clear now, but I will give a very simple example for a quotient space that I hope it will help you understand what it is. Yeah, but what's important for you to know is that now every element of the quotient space is an equivalence class, and in our case, we will denote it by this double ket, 0 and 1. And therefore, the map becomes now, as I said, now considering this quotient space, we can invert it. So now we go from the, and maybe this is a poor choice of notation. I apologize. This S maybe should be another letter, but now this is generally for composite systems. Okay. Yeah. So this is how the map looks now. Yeah. And then the first thing that you learn is that by consistently extending an isomorphism between complex and real numbers such that ambiguity is present in quantum mechanics, like global phase ambiguity and local phase ambiguity, if you keep those ambiguities present, then the structure of the resulting Hilbert space is imposed to you. And in particular, it's not a tensor product, it's this quotient space, which is it's not radically different from the tensor product, but it's not the same. Okay, so as I said, I promised that I would give you a little bit of intuition of what a quotient space is. And yeah, consider you have a function which takes the value 0 for every element in the vertical, in the y-axis. So every point in the vertical line in this y-axis is 0. So this function is highly non-invertible because you have a very large kernel, if you like. Every point in the vertical line is an element of the kernel. So what can you do to invert this function? You say, okay, I will consider all the points in the vertical line as the same element. So now this is your space, R2 quotient by y, sorry, is the space of vertical lines. And now in this new space, your function is invertible because the only element in the kernel is this vertical line that crosses the center. So this is the intuition behind quotient spaces and why they allow you to invert non-invertible functions. Cool. But in practice, one wants to work with vectors. And I told you that we have equivalence classes. So what do you do with them? There is a standard procedure which is called canonical representatives of equivalence classes. And this is choosing the particular element of every equivalence class. How do you choose it? You choose the vectors orthogonal to the space you are taking the quotient by. And this in our example, so now you take the space you're taking the quotient by, which is y. You take the orthogonal complement of this space, which is x, and you project every element of the equivalence class into x. So for this space, the canonical representatives of these equivalence classes are the vectors crossing the x-axis. So all of these points that hopefully you're seeing my mouse pointing are the canonical representatives of these equivalence classes. And these are vectors. Okay. And then, yes, you believe me because this is straightforward calculation that for our particular case, for this quotient space R4, kernel S minus 2 to the tensor 2, the canonical representatives are given by these states, which we denote even and odd, because they are this particular superposition of states with the same parity of ones, so even parity and odd parity. And I'm sure that many of you already recognize these states, and they resemble entangled states, but they are not. They are similar to fermionic or bosonic antisymmetrized wave function. So, and this is interpreted not as entanglement, but as a new type of indistinguishability relation. So now our postulates for quantum mechanics in the real vector space, the three first postulates remain the same because we haven't changed anything. We're still working with vectors, projectors are still well behaved, and you can measure probabilities in the same way. But now the fourth postulate, the composition rule, is the one that is different. So now we don't have, as I told you before, we don't have tensor product because, yeah, we are restricted. But then we want, as I said at the very beginning, we still want to have this notion of locality, or in the sense of things being only locally accessible. And this is formalized. Some of you are familiar with quantum field theory. This is the usual way one postulates locality or causality. So essentially, given two subsystems A and B, the operators used to describe measurements and transformations on A act trivially on B and vice versa, and this is given by the commutation rule.
So can I interrupt and ask a small question? So
Sure.
for instance, we don't really know, right, whether the tensor product and the commuting representation are equivalent, right? We don't, like, so commuting seems to be more general.
For finite dimensions, they are the same, right?
For finite dimensions, yes, but I thought are we restricting to finite dimensions in your analysis, or?
No, a priori no, a priori not, but I mean, yeah.
Okay, so one doesn't have to worry about these crazy things with infinite dimensions in drawing the conclusions in your work?
Yeah,
or?
Yeah. This is actually something that we became aware, but this is a question that we were interested after working on this. What happens with infinite dimensions? So basically, this zero-sum problem is what you're asking about, right?
Yeah, some variant of it. Yeah, I'm also not very familiar. I just know that there are subtleties and one needs to be careful. That's why I was asking. I'm not very, Yeah.
Yeah. So for finite dimensions, nothing new happens. For infinite dimensions, I have a conjecture that nothing new happens. So still, you can reproduce everything. Yeah. But this is nevertheless an interesting question. Yeah, like to see it.
I see.
Yes, it's a good question. Yeah.
Thanks. Yeah.
Mm-hmm. Yes. Okay. So in our model of real quantum mechanics, some usual properties arise, like density operators can be well defined. You can define a suitable partial trace. Unitary operators are mapped to orthogonal operators, and then you can also meaningfully define entanglement and many other properties. The physical implications is that experimental statistics remain identical, which basically this is the condition that I gave you at the beginning for two theories to be equivalent, which means that you cannot distinguish them in the laboratory. And yeah, in particular, local operators do not change local observations of other parties. However, the tensor product structure for representation in real Hilbert space does not match the properties of quantum mechanics in complex Hilbert space. Within our formalism, all expectation values of observables described in real Hilbert space are identical, and arbitrary multipartite quantum experiments can be formulated without the use of complex numbers. And therefore, the ultimate conclusion is that nature does not need complex numbers. And then as a summary, to maybe try to solidify the results that I have presented, we provide a map from complex to real vector spaces via the quotient space. This is done by extending a very well-known isomorphism between complex and real numbers, extending it to tensor product while keeping, let's say, the physical ambiguities that are present in standard quantum mechanics, like the global phase and the local phase. Yes, this is the next point. Yeah, so the ambiguities in the complex tensor product formalism induce a non-tensor product structure in the real vector space. However, we are able to formulate postulates for quantum mechanics arising from physical principles instead of from mathematical principles like the tensor product, because in the end, what you want is this locality. And of course, the tensor product grants you this locality, but we have seen that we can still have locality without the tensor product. Yes, yes, and our model of real quantum mechanics, as I said, preserves locality and crucially does not contradict any experimental observations, and therefore we do not need complex numbers in quantum mechanics. But as a side note, I would like to say that quantum mechanics is so much easier to describe using complex numbers. Yeah. And of course, if you are more interested in the papers and in the details where all of these things that maybe I have glazed through are proved in detail, you can check the preprint. And that's my presentation, and I would be very happy to answer questions. Thank you for your attention.